All right. So I just wanted to make y'all this little video because I know that we didn't have much time in class during Module 3, and then you have an assignment for Module 4 that kind of deals with some probabilities. We were able to cover some of those, but there are things that go on with this normal distribution that we talked about that we probably want a little bit of a better understanding on. So I'm going to show you real quick is how do we read Z tables and kind of what do they tell us? And then we're going to take a look at the Z table that I have. We'll take a look at a problem that shows up in the assignment that we have. And then we'll just take a look at some other notation that we might see. It won't be very long for this video. So the concept of that normal distribution was we can take any normal distribution that exists, and if we convert things to Z values, we end up in a distribution where the mean is 0 and the standard deviation is 1. And so the benefit of this is that we basically have a transformation that we make, and then it allows us to find areas under curves for a single normal distribution as opposed to an infinite number, right? And the reason why the area under the curve is important to us is because it's the way that we quantify the probability of seeing things happen. So we have this Z table right here. And what this Z table represents is I have my Z score. First two digits fall on the very left. Third digit of the number falls on top. So for example, if I was looking at the Z score of 1.25, I would come down this left-hand column down to 1.2, and then I would move across until I got to the 0.05. So 1.25 is how I would figure out what that little decimal value is. So that's how I determine which little part in this chart I should look at based on a Z score that I have. And then what this tells me inside is the proportion of data that falls to the left of that value. It's the proportion of data that falls to the left. It's also the area under the curve. Those are the same things. So the values in the middle of this table tell me the area under the curve to the left, the proportion of data that is less than that value. So that's what this table tells us. There's a positive and there's a negative sign. And so these are just areas under the curve to the left. So it's not too difficult for us to find those areas if we have this table. But there's maybe 3 different scenarios we would be interested in looking at. The first one is simply find the area under the curve to the left. Then we just go straight to this table. We look up the values. It's a very simple process. If we want to find the area under the curve to the right of Z, so instead of just the area under the curve to the left, I want to know area under the curve to the right. All we do is we look up the value on the table just like we did with area to the left, and then we subtract that value from 1. So we look it up and we subtract that value from 1. If I want to find the area between two values, what we do is we find the Z score for both of the values, and then I subtract the smaller one from the larger one. And that will give me the area in between those two values. So area to the left, look up the value on the table. Area to the right, look up the value on the table, subtract it from 1. Area under the curve between two values, look up both values, and subtract the smaller area from the larger area. So we'll take a quick look at those things on the board if we want to have a visual of kind of what we're taking a look at when we come to those things. So that first scenario said I've got my Z value here. Let's find the area under the curve to the left. So this comes from the value we look up on the Z table. And we'll look at an example right now. What other notation we might see when it comes to this? This is area under the left of Z. This is the proportion of data that falls to the left of Z. We might actually see something that looks like this. the probability that our z value is less than or equal to whatever this value happens to be. So let's say that this is 1.50. Then I would say that this area under the curve right here is the probability that z is less than or equal to 1.5. So that says find this area right. So what we do then is we go to our z table that we had, and right here, and I say, okay, area to the left under the curve of 1.50. So I start with my z. I come down to 1.5 because that's the first two digits. And then if that second digit is 0, second decimal is 0, well, then I just use this first column right here. So 1.50, 0.9332. So my area under the curve to the left is 0.9332. The probability that z is less than or equal to 1.5 is also 0.9322. Or sorry, 9332. So that's kind of how we go about using that table in the simple form of finding the area to the left. Look up that value. In the scenario where we want to find the area under the curve to the right. So maybe we have this scenario right here where we want to find that. So what we do in this scenario is I take 1 minus the value I see on the z table. So this shaded area right here represents area under the curve to the right, or the proportion of data that falls above it, or the probability of seeing the z-score larger than what we have right here. So in this case, on the first example, it was the probability that z was less than or equal to 1.5. Well, now I'm looking at larger than. This is the probability that z is greater than or equal to 1.50, if we're assuming that's the same value we just had. So how do I figure this one out? Right, we go back to that table and we look up that z value, the area to the left. Well, the area to the left of 1.5 was 0.9332. So I know that this area over here is 0.9332. The area over here will just be 1 minus that value. The total area under the curve of this distribution here is 1. So if I have this region plus this region plus this region, it will equal 1. So that's where we get that 1 minus right. So 1 minus 0.9332 becomes 0.0668. So the probability that z is greater than or equal to 1.5 would be 0.0668. And that's how we would go about looking up areas to the right. Now, in the scenario where I say I want to find the area between two z-scores, area between, what I'm going to do in this case is we'll just pick some values here. Let's call this z equals -1, and maybe z equals +1. So maybe I want to find out z between -1 and +1 and kind of see what the area in between those two values happens to be. So this is the region I'm taking a look at. Here's what I go about. Parse this off here. First thing I want to do is I want to find for z equals 1. I want to find the area under the curve to the left. For z equals -1, I want to do the same thing. So let's go and find the area under the curve to the left of z equals 1 using that z table that we happen to have. Area under the curve to the left of z equals 1. So I come down here, 1.0, I'm using that first column. 0.8413. 0.8413. Then I wanted to find the area under the curve to the left of -1. So -1, I come to the negative table, -1.0. Since I don't have a third digit there, I'm going to use this first column right here, 0.1587. 0.1587. So now that I've looked up both of those values, I can find the area under the curve here in between 1 and -1. So my first value, I had 0.8413. My second value is 0.1587. So I'm going to take 0.8413 minus 0.1587. And that's going to give me that area under the curve in between those two values. So we go to our calculator and we see that we get, when I do that, 0.6826. So that's how we can find areas under the curve in between. Now, probability notation. I didn't write that up here yet. So the probability notation in this case right here would be the probability that Z falls in between 1 and -1. So it would say -1 less than or equal to Z less than or equal to 1. So the Z falls right in between the -1 and 1. And so we take a look at that region right there using the probability. So that's kind of how we go about using the Z table that I provide y'all in class, and then finding areas under the curve to the left, areas under the curve to the right, and areas in between two values on that Z curve. So now let's take a look at maybe something you might see in your homework. Maybe you'll see problems that kind of look like this, right? So this is just kind of a straightforward example where we'll say, okay, find these following probabilities. Probability that Z is greater than 2.1. So when I take a look at the notation we just talked about here, the probability that Z is greater than a value tells me I need to look up the area to the right. So in that problem that we just saw right there, we said Z equals 2.1, and I want to find the probability that Z is greater than 2.1. So what I'm going to do is I'm going to find that area under the curve to the right. So what we can do now is we can go to our table, and we can use this to help us figure out what that value is going to be. So if I'm finding the area under the curve to the right, our method was look up the Z-score, 2.1, 2.10, find the area under the curve to the left, what the table says. That tells me it's 0.9821. So once we have this area under the curve to the left, I find the area under the curve to the right by subtracting that value from 1. So 1 minus 0.9821 tells me that this should be 0.0179. And so that's how we use our Z table to answer questions like that. Now, this is the Z table that I like to use. It's the one I've been using my entire life. It's the one I learned on, but it is not the one that is given to you in your textbook, right? In your textbook, they have this little Z table that gives you a proportion in the body, proportion in the tail, and the proportion between the mean and Z. So it gives you 3 different measurements. And the reason why I don't like it for y'all is that it gets a little confusing because it uses one table, but then it tells you that columns flip when there's negative numbers involved. This is actually a really useful and good table once you start getting a strong grasp of the material that we're taking a look at. But it becomes a little challenging for us to learn conceptually until we really understand it well. So if we take a look here, I'm taking a look at what this table is telling me. This is the area in the body, right? That's the area to the left. Area to the right is found in the proportion of the tail, C. So in this case, this problem is actually not too bad, right? Probability that Z is greater than or equal to 2.1. We just did the math and found out this was the value, right? 0.0179. If I were to use this table, what I would have to do is go, okay, 2.1, that falls between 2 and 2.24. Let me come down to 2.1 right here, right? And so we came down here and I would say, okay, I'm not trying to find the area in the body. I'm trying to find the area in the tail. Therefore, my answer is 0.0179. So that's how we would go about doing that, using this table. Now, where it gets a little bit tricky, right, is once we get to the negative value. Find the probability that Z is greater than negative 2.6. If I'm using this one right here, this table, I need to go to the 2.6 value. 2.6 value right here. Now, what happens is because I'm taking a look at a negative number, the tail and the body flip. But this doesn't really give you a good representation of that, right? So what you would do is say, okay, negative 2.6, the probability that Z is greater than negative 2.6. Well, this image on the left here kind of flips around. So the proportion in the tail is now equal to the proportion in the body, and the proportion in the body becomes the proportion in the tail because this is a negative number. So the answer to this is actually going to be 0.9953. That will be that probability that we have going forward. My recommendation, again, because that conversation I just had with myself, and eventually y'all that watch this, is a little confusing, right? Because of how we're identifying the body and the tail. So when it's on the right side, the tail's formed on the right. When our Z-score is on the left side, or a negative value, there's a tail formed on the left. And so that's the concept of how we do some of those problems right there. So hopefully that helps you a little bit. One more thing I want to show y'all on this video, I guess I got to get a rag here to kind of wipe off the board, is some other notation, maybe a problem that takes us an extra step or two as we're going about doing these things. So suppose I have a situation where, and there'll probably be a word problem associated with this, where it'll say, we have a distribution and the mean is equal to 100 and the standard deviation that we have is equal to 25. What is the probability that we measure something from this distribution and it is greater than or equal to 135? So this is kind of the question that we might see on a problem, right? We have a distribution, the mean is 100, standard deviation is 25. We randomly select something and it's 135. What's the probability of seeing something that is greater than or equal to 135 by a random chance? So we think about kind of what this distribution looks like. We have a normal distribution, the mean's equal to 100. And we're taking a look at a measurement score of 135. Probability that X is greater than or equal to 135, greater than or equal, says find this area under the curve to the right. Now, we talked about this earlier. There's an infinite number of normal distributions, right? So if we have one, we can find this area under the curve. If we have the appropriate tool set, maybe Excel can help us. There's applets online. But what we'll have to do for a problem like this is convert it from this distribution into our Z distribution. So now I want to convert this from a mean of 100, standard deviation of 25, to the mean of 100 and sigma equal to 25. So we're going to go over here and I say, okay, This score of 135 on this distribution corresponds to some z value on my standard normal distribution. So how do I figure out what that value is? I calculate, right? Z equals x minus mu over sigma. So in this case right here, x is 135, mu is 100, sigma is 25. So when I do that math, I get 35 over 25, which gives me 7/5, which reduces down into 1.4. So measurement score of 135 in this distribution corresponds to a z-score of 1.4. So I'm still trying to find the probability that x is greater than or equal to 135, which is equivalent to the probability that z is greater than or equal to 4. So now we can go back, use our z table to answer this question that we see. And we'll see that, okay, 1.4, I want to find the area under the curve that the table tells me, and then I'm going to subtract it from 1. So 1.4, the area under the curve to the left, 0.9192. So 0.9192, the table tells me it's the area under the curve to the left, and then I just subtract that from 1 to find this area under the curve to the right, 0.0808. And so that's my probability, 0.0808. And so that's how we go about doing that. Now, concepts that are going to come from this, looking up these values, calculating these things, are when we see values like this, the probability of seeing something like this or more extreme is roughly 8% of the time, right? Is that likely? Is it unlikely? Is it unlikely enough that maybe we're concerned about things, right? So those are some concepts that we happen to have. Now, this all gets changed a little bit once we start introducing the sample mean. If we recall from last class, there was the sample mean, the central limit theorem that told us that the sampling distribution of the sample mean was approximately normal, right? And then that z-score changed a little. So we'll be able to do some more practice with those as we go along and as we kind of learn these things, and as y'all do your discussion posts as well. So that's what I've got for you. Just a quick and basic example of how we read those tables, the ones that you might see in your exam, sorry, not exam, in your homework. And then, you know, a couple of examples of other problems we might see that may look a little confusing when we start, but really at the end of the day, it all boils down to finding areas under the curve of the z distribution. So that's it. I'll see y'all in class.